Welcome to the Global Composites Experts webinar series. My name is Wenbi Yu, Director of the Composite Design and Manufacturing Hub. This webinar series is to examine the history, present capabilities, and future of composites with the goal of sharing the knowledge of composites that has been developed over the past 50 years. This webinar series was initiated by the Composite Manufacturing and Simulation Center at Purdue University. We are located in this beautiful Indiana Manufacturing Institute. All of you are welcome to visit us when life returns to normal and it is safe for us to travel. We launched the CDM Hub in 2013 with the mission to convene and serve the global composite community by creation, education, evaluation, and sharing of resources for composite design and manufacturing. CDM Hub provides a very powerful website called cdmhub.org for the composite community to carry out this mission together. We envision CDM Hub to become the premier resource for composite design and manufacturing in the near future. This webinar series is one of the initiatives CDM Hub started as a service to the community. This webinar series is made available by the support of CDM Hub sponsors, including Dassault Systems, Cytec Survey, MAC Software, and Modex 3D. We greatly appreciate their financial support for CDM Hub. Next, I will show a brief commercial from one of our sponsors.
In case you are wondering, you are not fighting molding defects alone. Introducing Modex 3D, your plastic injection solution. With powerful molding simulation features, friendly and easy-to-use interface, Modex 3D pinpoints design problems before production and achieve better product quality with less time, less cost, and less waste. Modex 3D, the best partner for plastic industries.
Thanks again for our sponsors' support. We invite more organizations to join them to serve the global composite community together. This webinar will be recorded and made available on CDM Hub. An email will be sent to you once the recorded video is available online. The presentation will last about 40 minutes and will have about 15 minutes for Q&A. All attendees are muted. Please submit your questions through the Q&A box. After the speaker's presentation, your questions will be read and answered. Next, I will ask Dr. Pipes to introduce our distinguished speaker today.
Greetings, everyone. I'm delighted to introduce Professor Conchur Bradaigh, head of the School of Engineering at the University of Edinburgh. Professor Bradaigh joined the faculty of University College Galway, now the National University of Ireland, Galway, as a lecturer in 1991, and he led the Composites Research Unit there from 1993 to 2008. He rose to the rank of senior lecturer in 1999 before becoming and founding co-managing director of Erie Composites in 2002, a company that specializes in thermoplastics composites manufacturing. He took a leave of absence from his academic position in 2002 and participated in a growing Erie Composites to become a leading innovator in the development of new composites manufacturing technology. Its clients included aerospace manufacturers throughout the world, including Bombardier Aerospace, Airbus, and Eurocopter, and its products have gained widespread recognition for their performance and economy. The company currently employs 60 people and is the only aerospace accredited composites company in the Republic of Ireland. Dr. O'Brady returned to academia in 2010, and he held faculty positions at the University of Ireland, Galway, and Cork. At the University College Cork, he was director of the Marine Renewable Energy Ireland Centre. During this period, he and his students worked on the development of composites technology for offshore energy harvesting. He was named Chair of Materials Engineering and Director of the Mechanical Engineering discipline at the University of Edinburgh in 2015. And in 2018, O'Brady was named head of the School of Engineering at the University of Edinburgh, where he leads programs in 7 engineering disciplines and 7 research institutes. In 2008, he received the inaugural Sir Bernard Crosland Medal for Engineering Innovation. His seminal contributions to high-performance thermoplastic composite materials and structures have established him as a major force in this emerging and important field of study. I am delighted to offer the podium to Dr. Conchur O'Brady.
Thank you, Byron. And I'd like to say thanks to Byron and to his team at Purdue University for inviting me to take part in this webinar series. I'm deeply honored, given the caliber of the people that have spoken before and after me in this series. What I'm going to talk to you today about is the use of novel powder epoxy materials for thick section structural composite materials. This is an outline of my presentation. I'm first of all going to talk about the rationale and the impetus for developing these rather novel materials for the manufacture of renewable energy structures such as wind turbine blades and tidal turbine blades. I'm going to introduce the materials as a composite matrix. I'm going to describe the simulation and experimental work that we've done in gaining a better understanding of how to process thick sections with these materials. And I'm going to introduce a novel technology for surface toughening of renewable energy blades such as wind blades and tidal blades. First of all, I'd like to acknowledge my students and my postdoctoral researchers and colleagues, all of whom helped in the development of this work, and I'll acknowledge 1 or 2 of them in particular as I go through. I'd also like to acknowledge the industrial sponsors and funders of this work, which was funded most notably through 2 European Union funded projects, Marencomp and Powderblade. And you can see there the logos of the industrial and academic partners who were involved in that work. I'd also like to acknowledge the EPSRC UK Future Composites Manufacturing Research Hub, or SimComp, which is funding some of the more recent work that we're doing on powder epoxy materials for tape placement. So first of all, let's talk about tidal energy. We have quite a lot of tidal energy, which is a clean, renewable energy source, but is largely unexploited, particularly on the west coast of Europe, around the islands of Britain and Ireland. And shown here in pictures are 2 types of tidal turbines. The one on the left is a French device, which sits on the seabed and operates like an underwater wind turbine. The one on the right, no, it's not a boat. It's actually a floating tidal turbine, which is moored. That turbine isn't moving, and it just gives you an idea of the strength of the tide as it flows through the Pentland Firth at the north of Scotland. So this is a predictable and dispatchable, from a utilities point of view, energy source. Unlike wind energy, it's invisible, it's underwater. Some of the drawbacks are that it varies over small geographical spaces, and of course can be difficult to access and maintain, and you have challenging conditions at sea. So what about the blades? Well, composite tidal turbine blades, like wind turbine blades, are manufactured in a very similar way. However, the main difference is that the power that flows through a device like this is linearly related to the density of the fluid. And as water is 100 times more dense than air, then you have a lot more force, thrust force, and torque coming through the turbine blades. As a result, they're quite a lot shorter than an equivalent wind turbine blade. They also have more challenging conditions at sea, such as erosion from ice and sand, and also dealing with waves and storms in the case of a floating turbine. The blades, of course, require very high strengths in terms of static and fatigue performance. They tend to have very thick composite sections around the hubs, up to and over 100 millimeters. Developers are investigating the use of both carbon fibre and glass fibre at present, and of course water ingress degradation as these blades live under the sea for 20 years, is quite important. Add in the additional costs of repairing and accessing particularly the seabed mounted turbines, and you can see that we really need very good materials and very good design and testing facilities for these materials. This is just a slide to show that the University of Edinburgh in May of this year will be commissioning the world's first dedicated tidal turbine fatigue test facility. This is at the premises of our partner Babcock International Group in Rosyth in Fife here in Scotland. And what's unique about this particular facility is that we're going to be using for the first time a new type of regenerative hydraulic pumping, which greatly improves the efficiency of the hydraulic pumping and structural testing setup. This is done by storing the strain energy from the blades after each cycle in the pumping system of the hydraulics. So this will be handed over to us and will be commissioned over the summer. So moving on to what are powder epoxy composites and why are we interested in using these materials for thick section composites? One of the main reasons that we're interested in this material is the use of standard liquid composite epoxy resins tends to result in thermal overshoot if the materials are not processed in the correct fashion. And this particular graph here from a 1993 paper shows the strong dependence of the thermal overshoot on the thickness of the parts. This is a 30 centimeter part here. Imagine how much more of a thermal overshoot you'll get with a 100 centimeter thick part. These thermal gradients can cause warpage, residual stresses, microcracking, and in some cases even fire. So what are powder epoxies? Well, powder epoxies are commodity materials that have been available on the market for decades, but are typically used for the powder coating of white goods and other metal structures. The epoxy is solid at room temperature. If we look at this DSC scan here, we'll see that we get a melting somewhere in the region of 50, 60 degrees centigrade. You then don't get any further heat released as you heat until you reach a cure peak around 160 to 180 degrees centigrade. So there's quite a distance between the melting peak and the cure peak. And what this allows us to do is to heat the powder 50 degrees centigrade. It becomes viscous. The viscosity is shown here on the right. We can consolidate the parts at that temperature. We can indeed cool them down and reassemble complex parts together and then reheat in order to carry out the final cure. So a typical one-stage cycle would be shown here, a ramp to 120 degrees centigrade, followed by a consolidation cycle, followed by a ramp to eventual cure. One of the big advantages of the materials are the very low minimal viscosity. This is about 1 Pascal seconds here at the lowest point, which means that it's easy to infiltrate and wet out thick fiber beds. These materials, because they cure, they're thermally activated, so they take the thermal energy from the oven, the tool, in order to cure. This means that they have a very low curing exotherm, which is very advantageous when processing thick section composites. We look at the total enthalpy of reaction of different epoxy resin systems. You can see that many of the resin transfer molding, resin film infusion, pre-peg materials have enthalpies of the order of 400 to 500 joules per gram. This is the energy contained in the reaction to carry out the cure. In contrast, the powder epoxy materials have about an order of magnitude less enthalpy of reaction, which is what makes them particularly suitable for processing thick sections. Furthermore, they're widely available and relatively inexpensive and generate little or no volatile organic compounds during the process. So combined with low viscosity, low exotherm, you never get any dry spots because we typically do a through thickness infiltration. Shown down here is a glass semiempirical material where we have deposited the solid powder and heated to melt onto one side of a glass fabric. This makes it easy to handle and also provides pathways for vacuum exfiltration of air during the consolidation process. And as I mentioned earlier, you can consolidate uncured structures by exploiting the temperature difference between the melt point and the curing point of the resins. This particular wind turbine blade section here was co-cured from 3 pre-consolidated glass fiber powder epoxy semi-preg pieces without any gluing or other points which could be weak points for failure. Just to look at some of the industrial applications, the company which Byron mentioned that I was involved with and founded, Era Composites in Galway, in Ireland, is producing wind turbine blades. Also, a tidal turbine blade shown over here being tested at my old university, NUI Galway. And in that case, it was using electrically heated tooling. You can see here a typical bolt pull-out test section showing the monolithic thickness of the material at the root end. So there are a lot of industrial advantages: one-shot cure, no gluing of spars. You don't have to store the tow-preg in any particular environment, and it's easily quality controlled and upscaled for industrial purposes. As I said, the materials are commodities and are available. Nonetheless, at the University of Edinburgh, we have a very good partner in Switzerland, Swiss CMT. I'd like to acknowledge Marcel Schubiger's support in providing different types of powder resins, and he has quite a nice business in developing this technology for infrastructure, renewable energy, and other automotive applications. Just to show you some work which we did through one of our EU projects, where we're carrying out testing on a 6-meter torsion box. This box was designed by our wind energy partner, Suzlon Blades. And you can see on the inboard section here is a glass fiber powder epoxy section, and on the outboard section is a carbon fiber epoxy section. And during this fatigue testing, we were investigating the quality of the joint between the glass and carbon using 3D digital image correlation and also traditional strain gauges. So moving on to how we developed an understanding of the processing of these materials. I'd like to acknowledge my PhD student, now postdoc, Dr. James Maguire. And this was largely his PhD. And his aim was to improve the quality and reliability of the processing of thick section structures from these materials. This involved experimentally characterizing the epoxy powder, developing material models, putting all the models together with the heat transfer model to understand the processing of thick section composites, implementing these models in commercial simulation software, and then validating the process simulations experimentally. So the 4 steps shown on the left there are the material modeling that James carried out. I should say that this work was funded by the MarinComp EU project, and there's a paper in Materials and Design from 2018 which has all of the details. So the first step was to look at modeling the cure kinetics. You can see the isothermal cure. The circles are the experimental points, the symbols, whereas the solid lines are the model fit. So you can see the difference between curing, degree of cure against time at 160, 170, and 180 degrees centigrade. There's also a relationship between the glass transition temperature and the degree of cure of the material. And we were able to measure this experimentally and also fit it with a suitable equation. We had to consider the sintering of the powder, how it melts, and we measured the powder void fraction. You can see it from 0 to 0.5, starts at 0.5 and drops off towards 0, depending on the temperature at which the sintering is happening, typically around 50 to 60 degrees centigrade. And again, that was fit with a suitable equation. And finally, we characterized the viscosity of the powder epoxy at different rates and at different temperatures. The next step in the process then was to look to see how these individual material models would predict the behavior of the epoxy on a complex cure cycle. So you can see here the degree of cure evolution for a simple ramp to 120 degrees centigrade. And you can see what happens to the viscosity as it drops with heating, and then as it starts to cure, you get an increase in viscosity. A typical industrial process involves separate consolidation and cure cycles. So you might take the bottom skin of this blade section and you heat it to 120 degrees centigrade, consolidate it fully, then cool it down and bring it together with other parts in the mold for the eventual cure. So that involves a thermal cycle whereby the temperature is raised, kept at a dwell, dropped again to room temperature, then raised again, and then fully raised in a ramp to cure. And you can see here a comparison between the viscosity and cure models against the actual measured performance of the resin. And you see a very good fit to the chemo-rheological properties. So we then needed to develop consolidation and thermal model for the processing of thick sections comprised of alternating layers of glass fiber and powder epoxy. So if we look very closely at the structure of this material before it's heated, before vacuum is applied, you can see that we've idealized here the dry toes with the pure resin layers in between, and you can see the air pockets in here. So the fundamental consolidation assumption here is that the intertoe flow, which is where the resin flows into these air pockets as the air is removed by vacuum. This is the easier flow to happen because of the very low permeability. And therefore, the assumption is that this intertoe flow occurs first before the intratoe flow occurs, with the resin flowing into the fiber bundles. In some work that my student did, James McGuire, with Professor Suresh Advani at the Centre for Composite Materials and his team, we developed a one-dimensional flow model. So we idealized these flows as occurring in the true thickness direction of the thick section composites. And we combined this with a heat transfer model, which considered the thermal resistance of the different layers to be in series with each other. Clearly, this is a moving boundary problem, as the resin, pure resin here, infiltrates into the permeated region of the intertoes and then into the intratoes, and then permeates into the intratoe region. And clearly there is a change of thickness of the overall laminate. We can model the intertoe flow and the intratoe flow using suitable Darcy law equations. And these are valid in the different regions. We then integrate all of that together to form a moving boundary problem and are able to calculate the reduction in thickness when the vacuum pressure is applied. We use a one-dimensional heat transfer equation with a heat generation term, which comes from the activity of the resin. And we then couple the solution of this one-dimensional finite difference thermal model with a flow model and simultaneous thickness updating. For those of you that are interested in the details of this, there are two papers, part 1 and part 2, published in Composites Part A journal in the second half of 2020. I'm going to show you some simulation results here, but before I do, I'll just show you this is the heating ramp, which is applied versus time. It's quite a long time there, so we're making sure that the material is fully dried and just making sure that everything is right. We then ramp to 120 degrees centigrade and then ramp further to 180 degrees centigrade. The black line shows the simulation predicted reduction in thickness of the material as it consolidates. If we look then at the results, we'd see this is a plot of temperature as the thickness reduces, and up here is a contour plot of degree of cure. So you can see that things are pretty stable until the first ramp. Then the material heats from the outside, cures from the outside, and finally comes to its steady state value. If we look at the distribution of temperature through the thickness here, we can see that at certain stages of the process, you can get quite large differences in temperature between the outer surfaces and the inner surfaces of the 100 millimeter thick composite laminate, which is understandable. So then we looked to experimentally validate the model. and we set up a one-dimensional measurement system whereby we have our stack of glass fiber and powder. This is loose powder in this particular case. In this particular case, it's a semi-preg material where the powder has been somewhat infiltrated into the glass layers before processing. We then vacuum bag that, applied suitable thermal insulation, and then used a linear variable differential transformer to measure the thickness of the stack as it was processed. We also applied a series of K-type thermocouples through the thickness so we could measure the temperature profiles. This is the final laminate before debagging, and here is the final laminate when processed. If we compare the in this first plot on the left, we have a comparison. This is our thermal cycle shown here on the outside, and the equivalent colored dotted lines are the experimental results, and the simulation lines are the solid results. You can see an excellent correlation of temperature throughout the processing of the laminate. On the right-hand side here, we can see the thickness distribution as measured by the dotted line here and as simulated by the solid line. So again, I would say not quite as close as the thermal simulation, but quite close. We then looked in a bit more detail at the temperature differences and also the degree of cure differences during the process. And shown in these colored lines here are the degree of cure simulated results for different points in the process. And we can see that in particular at the onset of the full cure here, you can see that with a gel point of about 0.56, you can see that we have quite a difference in time needed for the different parts of the laminate to get to this gel point. So what this actually means is that the outside of the laminate is gelling and curing before the inside of the laminate, which can cause problems. And if we look at the maximum difference of degree of cure on the vertical axis here versus time, and the maximum difference of temperature here, you can see that when the final temperature ramp is attempted, the temperature difference increases, and you can see that the difference in degree of cure increases as well. So we believe that this type of difference in cure profile at such a point would be damaging for the laminate. So as a result, we proposed a slightly different process cycle, whereby we shortened the drying cycle and we increased the time required to go from 120 degrees centigrade to 180 degrees centigrade. And you can see that result here is to bring the ISO cure lines much closer together. And indeed, we could drop the maximum temperature difference almost to zero and drop the degree of cure difference quite a bit. So I think this is an example of where careful simulation and experimental verification can improve the processing of these types of laminates. My PhD student, James Maguire, then got the opportunity with the funding from the Royal Society of Edinburgh to spend 3 months at Purdue University at the Composites Centre with Professor Pipes. And the work that he achieved there was to take the one-dimensional finite difference work that he had done and to implement these models into an abacus finite element analysis. And this was very successfully carried out. What he did was to perform 2D and 3D heat transfer simulations while still keeping the one-dimensional nature of the flow. And this resulted in some very interesting results. These are some of the components that he modeled to look at the difference. This is what we call a one-dimensional flow cube, which was used to validate and compare to do the three-dimensional heat transfer simulation to compare with the previous one-dimensional finite difference simulations. And indeed, the results were very, very good, in particular for glass fiber laminates. Shown on the right here then is a section of a wind turbine or tidal turbine blade hub. And you can see the variation in thickness from the thick end here as it tapers down to a point. And this section of this is shown over here, and we'll carry out an analysis on that as well. So as I said, the comparison between the finite difference and finite element models were quite good for glass fiber laminates. And these are the some of the simulations. So you can see on top the consolidation as well as the temperature profiles. And you can see that as the drying cycle continues, you get to a fairly stable situation, followed by rapid changes in temperature and followed by cure as it goes to 120 degrees centigrade, and then again as it goes to 180 degrees centigrade. We compared the temperature and degree of cure predictions at the center quarter of the laminate here to the one-dimensional predictions, and they were excellent. However, when we carried out an analysis of a carbon fiber one-dimensional cube with a three-dimensional heat transfer analysis, we noticed a number of things. First of all, this is the standard cycle shown here in the solid red line, drying followed by ramp to 120, followed by ramp to 180. And what we found with this is that the thickness of the carbon fiber laminate never got to where it should get. So we weren't able to achieve full consolidation. This is due to the reduced permeability of the carbon fiber toes compared to the glass fiber toes. However, when we simulated a modified thermal cycle where we had less drying, we had basically an increase to 120 degrees centigrade at an earlier stage, followed by a more gradual ramp to 180 degrees centigrade. And we did indeed achieve full consolidation according to the simulation. It was very interesting as well that when we compared the 1D analysis thermal profiles of the different plies to the thickness against the 3D analysis, for the carbon fiber laminates, we could see quite a difference. So the dotted line here is the 1D analysis, whereas the solid line is the 3D analysis. So I guess this shows the limitations perhaps of the 1D thermal analysis, in particular for carbon fiber laminates. Looking at the variable thickness wind or tidal turbine hub analysis then, we carried out an analysis on this. So this is 100 millimeters thick here, tapering down to practically a very thin laminate with the same convection boundary conditions applied on every surface. And you can see at a particular point here where cure is when we get to the high temperature, that there's quite a big temperature difference from the outside of the thick laminate to the center of the laminate, whereas the thin section of the laminate is quite uniform in temperature. We had a maximum temperature difference of 40 degrees centigrade, which resulted in a maximum degree of cure difference of 0.48, which again could cause process problems. We applied the modified cycle to these particular thick section structures, and we also applied a specified temperature boundary condition on the bottom end, which would model a heated tool, and also applied the equivalent of a heated blanket over the top section here and applied a specified temperature boundary condition here. We then left the rest of the hub section to be heated using convection conditions. And you can see here that we were able to reduce the previous 40 degrees centigrade difference to less than 7 degrees centigrade, and able to reduce the maximum degree of cure difference to approximately 0.07. So I think that this shows the efficacy and the use of these types of material simulations for predicting and improving the quality of laminates and structures. Okay, so the last topic I'd like to talk about is the issue of blade erosion or leading edge erosion, which occurs in wind turbine blades and also in tidal turbine blades. And this is a very well-known problem in wind turbine blades, where I would say that it's at this stage probably a problem which causes the industry hundreds of millions of dollars of damage every year. And essentially you have a large wind turbine blade shaped like an airfoil, which is traveling through the air, The tip speeds would be approximately just below supersonic. And as a result, when they meet droplets of rain, we get this leading edge erosion, which happens and causes a lot of damage to blades. You probably won't be surprised to know that with tidal turbine blades, we get the same problems. And this is a picture of a tidal turbine blade removed from the sea after about a year's operation. You can see the leading edge erosion here. And you can even see trailing edge erosion with this particular blade. So it's quite a serious problem. Collaborators of ours at the University of Strathclyde and Professor Margaret Stack have been studying this phenomenon in tidal turbine blades since probably for the last 6 or 7 years, and have been able to look in detail at, they've built an erosion rig, which I'll show you in a minute, which shoots a slurry of water, sodium chloride and sand particles at the composite, and then measures the mass loss on the surface. And they've been able to put together these erosion maps where the impact angle to the plate is plotted on the horizontal axis, and the size of the sand particles is plotted on the vertical axis, and being able to predict where in what conditions you get low erosion, what conditions medium, and what conditions severe. And you can see that on the left here is an uncoated composite, which is quite severe, and on the right is a coated composite. So clearly there are solutions out there for protecting these composites. And I'd like to acknowledge my Chancellor's Fellow, Dr. Colin Robert, who is also funded by the EPSRC Future Composites Manufacturing Hub. And Colin has been leading the powder epoxy development work to improve this surface erosion issue. And you can see here the standard application of a tough surface layer. In many cases, it would be a polyurethane tape or a polyurethane film. In this case, you have your core composite here, which provides the basic mechanical properties of the blade. And then you have a toughened layer on the surface. And of course, the problem with this is that you get problems at the interface between the toughened layer and the core composite. You get poor stress transfer due to the large mismatch in mechanical properties. This leads to decohesion as the toughened layer is worn away. Once it's removed, the core composite has no protection left. So this type of system is standard in the wind blade industry and is a source of a lot of cost in terms of repair. What we've developed is the use of different types of powder epoxy materials to produce a core composite which has stiff and good long-lasting static and fatigue mechanical properties, but in which the resin, the powder epoxy resin, is applied in layers so that we have a greater percentage of toughening agent in the powder as it approaches the surface. And the idea here is that instead of an interface, we have an interphase region, or you have a continuum of toughness in the composite from the core right out to the surface. And we believe this is the first time that this has been applied to try and solve this problem. We believe it will cause better stress transfer from impacts, better erosion fatigue behavior, and ultimately lead to lower costs for the wind energy and tidal energy businesses. We have a paper submitted to the journal Lubricants, which is just in revision at present. So we hope that this will be published pretty soon. Just looking at some of the issues with using different toughness contents of powder epoxy. So you can see here 3 different types of laminate. This one here has a 50% toughened epoxy composition of its resin. This one has a 25 toughened epoxy composition, and this one is 100% standard epoxy. And we carried out a series of mechanical tests, longitudinal tension, transverse tension, longitudinal compression, and we were able to plot on the right hand here. Just one of the examples is we were able to see a linear decrease in 0-degree tensile strength and in 0-degree tensile modulus as the percentage of toughened epoxy in the resin went from 0% or untoughened to 25% and up to 50%. And what's actually happening here is that a higher toughness epoxy has, because of its nature, a higher viscosity. And as we're processing thick section laminates, we only have vacuum to provide the consolidation pressure. Therefore, we rely on a low viscosity from the material to drive out all of the voids. So clearly, if you were to attempt to produce a fully 50% toughened epoxy sample, this is very difficult to do because of the high viscosity of the resin. This is the erosion rig. You can see here an outlet nozzle, you have a mixing chamber, and you have your composite specimen here on the right, and you impinge a jet onto the specimen and measure the mass loss. So you can see here we try at 15 degrees impact angle, 30, 45, 60, 75, and 90. And we also have 3 fiber orientations versus the jet angle, 0 degree, 45, and 90. And I'll just show this one plot of results. We can see here a comparison between the mass loss in grams versus the impingement angle for a standard powder epoxy glass fiber composite laminate, and you can see the improvement in the reduction in mass loss for the gradient toughened material. And in this particular case, the laminate had a gradient in toughness from 0% tough epoxy at one surface to 75% tough epoxy at the surface that was being impinged with the jet. And you can see more details on that in the paper when it's published. So one last slide just to finish up. I'd just like to mention Colin Robert's project funded by the EPSRC Future Composites Manufacturing Hub, where he is developing an automated tape line for production of powder epoxy prepreg tape. And this is currently underway. We have published some preliminary work in Composites Part B last year on the excellent properties we can get from this type of tape placement system. We're actually using, because of the carbon fibers in the process, we're actually using electrical joule heating for rapid heating of the carbon fibers, and we're using electrostatic attraction of the powder to the prepreg tape. And you can see more on this work in the 2 papers. And I'd like to acknowledge the EPSRC Future Composites Manufacturing Hub and our industrial partners for developing these materials with potential to use for industrial automated fiber placement. There are some references there if any of you are interested in following up on the particular papers that I referred to. And just like to finish up in summary, powder epoxy composites have advantages in processing thick section and multi-part co-cured composite structures. Full material characterization and thermofluids modeling has led to an understanding of how to process these materials in thick sections. And we've developed these gradient toughened materials for improved surface erosion resistance for wind turbine blades and tidal turbine blades. And finally, FastBlade will be the world's first dedicated tidal blade fatigue test facility when it opens in 2021. And as you can see from the picture behind me, we welcome you all to come to Edinburgh to meet with us and visit our facilities when it's safe to do so again. So with that, I'll take any questions that you have. Thank you very much.
Thank you, Professor O'Brady. I'm Jonathan Goodsell, and I will be directing questions here. We have a few, and there's a number of questions, as you wouldn't be surprised, about voids. You touched on that, both of the toughened systems. I'll consolidate these into an overall question: interest in void content currently existing in epoxy turbine blades, and how that's measured in actual production, and then some questions around differences between if you've seen differences between carbon fiber and glass fiber composites with void content, perhaps also dependent on thickness.
Yeah, I would say that the issue of void content in standard resin infusion systems for large wind turbine blades, I would say is a secondary issue. Probably a more important issue in wind turbine blades is actually the occurrence of dry spots. So this is areas where the resin infusion front separates for a particular reason, due to an inclusion or a wrinkle in the fabric or something like that, and then comes back together afterwards, and the dry spot is never actually filled. I would say that using large-scale resin infusion, from one end of the blade or from different points of the blade, is somewhat of a hit or miss application. Though I will defer to Professor Advani's previous talk in this series. No doubt the simulation tools are improving. However, it is difficult to avoid issues like fiber wrinkles, etc., which can then lead on to these dry spots. I would say one of the advantages of the powder epoxy systems is that as we're carrying out a through thickness infiltration, we never get dry spots, because the low viscosity of the material, essentially capillary forces, are enough to even cause full wetting out of the fabrics. The issue of voids is one that you can get if the material isn't properly consolidated before curing. But I think with proper understanding of the processing, and it is more problematic with the thicker sections, but with proper simulation, I think, and understanding of the process, you can certainly get around these problems.
Thank you. A question has come about consolidation wrinkle predictions. Have you been able to predict wrinkles during the consolidation process?
We haven't looked at that, but it's certainly would be perhaps one of the next steps in developing this simulation model. We're not actually modeling the mechanical response of the fabric during the simulation. So obviously the wrinkling occurs from an imbalance of forces, and from the fact that the fibers are long and thin. So when placed in compression, you certainly can get wrinkling. So it certainly would be a very nice addition to the type of simulation tools that are available.
Certainly. Taking a step back to look at maybe some of the big picture for a moment, a couple of questions on thermoplastics and using thermoplastics for tidal wind blades, including a question about has there been any effort based on reactive thermoplastics to produce?
Yes, I can say that the company I worked or founded in Ireland, I'm no longer involved with them, Composites, were the first to develop we developed a 12-meter wind turbine blade using the Cyclics CBT, which was a one-part powder system on a heated ceramic tool. That was around 2008 or so. Cyclics, unfortunately, are no longer in business. I would be quite enthusiastic about the helium systems from Arkema, which are room temperature polymerization, if you like. So a little bit different from the powder epoxy systems here in that they carry their own thermal energy in the form of chemical energy in terms of carrying out a full polymerization. But I know that there's a big nationally French-funded project underway, led by Arkema and LM Wind Power, to develop the helium technology for large wind turbine blades. And as far as I understand, that would be a large-scale resin infusion system at room temperature, but possibly may need to use heated tooling, because you have this balance between the chemical energy of the resin, which allows you to process at lower temperature tooling, but then the necessity to process thick sections. So you need to reduce that heat of enthalpy in order not to cause residual stress issues. So there's that balance between the two. But yes, we would be, I would be very optimistic about the prospects for that particular reactive thermoplastic resin for both wind turbine blades and tidal turbine blades. And I should say other large infrastructure and oil and gas and other large structures.
Can you comment maybe a little further on mold construction? There were some questions noticing that the cure temperature of 100 C was higher than what often most wind blades.
Yeah, that is one of the issues, obviously. And it is the weakness of the powder epoxy material for large industrial structures, as with the current chemistry that we're using, is that you do have to have a tool that's capable of going to 180 degrees centigrade. So I think that's probably more feasible at the tidal turbine blade type size of, right now the blades are maybe 8 to 12 meters in length, but it's difficult to see how you can take a 100 meter plus wind turbine tool to temperatures as high as 180 degrees centigrade. So that certainly is an issue.
Would a thermoplastic powder make any sense for this application?
Yes, indeed. And if anybody out there has got one, they've got my email address. I'd love to talk to them. I would say, sorry, I'm being a little bit facetious. We would need a thermoplastic powder which was going to react and polymerize in situ, as we had with the cyclics material. And the reason for that is that a standard thermoplastic, the reason we like thermoplastics is the increased toughness and the ability to recycle the structures and to weld, etc. But the reason these materials have an increased toughness is because of their long polymer chain length. Now, a long polymer chain also means you get a high viscosity. But you could see with the gradient toughness work we were doing with the powder epoxies that even with the 50% toughened powder epoxy material, it was difficult to process any kind of thickness of laminates under vacuum because the viscosity had increased so much. So we need a powder which can then melt and react in situ and then become a full thermoplastic so that we can wet out the large structures.
Makes sense. Another question on powders. Someone asked the question, the powder epoxy seems to have the perfect fit for this application. What are the possible disadvantages? You've touched on one with the tooling and the tooling material required.
I would say that a second disadvantage is potentially there isn't obviously a developed supply chain at present. I mentioned Swiss CMT, and we have a very good partner there, Marcel Schubiger, and also Freilacher in Germany, who are developing these materials. But these materials are largely and have been developed for powder coating applications. So I think in the absence of a developed supply chain, which hasn't come yet, it's difficult to see that the materials would be implemented and certified in large scale serial production. But I'm sure that there's a business opportunity there for somebody. From a technical point of view, I would say there are some issues around the hygroscopic nature of the powders. So James McGuire and our team have been doing some work in terms of the length of time that's necessary to make sure that you've expelled any water. So that drying cycle for the big structures. So that certainly probably needs a little bit more chemistry and needs a little bit more work. But we found that the absorption and desorption of water from the powders is quite easily understood and quite easily reversed. Of course, the production of a semiempirical type material, where you have less surface area of the powder, actually reduces that particular problem. So that certainly needs to be looked at.
Someone raised the question around repairability, especially with the gradient concept. How would you repair such a blade, and how would that differ with what's done today?
Yeah, I think you'd have the ability to perhaps using, as you say, the gradient materials. You certainly have the ability, because it's a true thickness infiltration, you have the ability to position your dry fabrics in whatever order you want them over a repair patch. You also have the ability to perhaps introduce layers that have materials that can produce a better bond with the parent material. And of course, you can have a heater blanket and heat the local area. So I think we haven't really started to look at that yet, but I think there are a number of different possibilities there. because of the fact that you can tailor the properties through the thickness.
Another question along the lines of this manufacturing, someone asked if there's potential to use the thick powder, the powder to fabricate a thick section like a root section, and then join that somehow with a conventionally infused epoxy blade. Could you?
Absolutely, and that's one of the things that Suzlon blades were looking at in the one of the big EU powder blade project, was actually the production of sub-elements, which were troublesome, or and then the introduction of those elements into a standard resin infusion cure cycle. Yes, that can certainly be done. Mm-hmm. One of the issues that also of interest is the production of these carbon fiber spar caps. So there are issues with the control of fiber straightness in carbon fiber spar caps. So if you obviously spend a lot of money on purchasing UD or UD stitched carbon fiber materials, but then you use a resin infusion process, which has the ability to produce localized wrinkles in your carbon fiber materials, then it negates the usefulness of that carbon fiber, because mechanical properties are so dependent on the fiber alignment. So that's one of the reasons that the wind turbine blade industry is invested heavily in the use of pultruded spar caps. But it could be that the powder epoxy material could actually be a kind of a halfway house between the two type systems, that you could actually do things with the powder epoxy that you wouldn't be able to do with either the resin system or the pultrusion system. So that's something we're also looking at present.
Are there aspects of these technologies that could be transferable to other industries, say to aerospace components?
I think the difficulty with aerospace components is that generally your even secondary structures in aerospace will typically require hot-wet properties. Mm. So you're looking at higher glass transition temperatures than we would have. Our typical glass transition temperatures with these powder epoxies, and also with most in situ polymerizable or reactable thermoplastics, would be, the powder epoxy is about 110 degrees centigrade. And most of your thermoplastic type materials we were discussing earlier would have glass transition temperatures of 50, 60, 70 degrees centigrade. So your kind of 120 degrees C hot wet requirement for aerospace would be very difficult to reach.
Makes sense. I'll ask a question about sizing. Someone wondered whether or not you'd need a new formulation of sizing for the powder epoxy to coat carbon or glass fibers.
No, indeed not. Two of the papers that I showed in the presentation deal in detail with the sizings. We had Torre Carbon Fibers were one of our partners in the Marincom project, and we were able to use standard sizings to achieve excellent mechanical properties and also excellent water degradation aging. So no need for any special sizings, just to use a standard type epoxy system. But you'll see it in the paper in the links that I gave.
Very good. Well, Professor Bradaigh, we thank you again. We'll close today's webinar here, and this will be made available on cdmhub.org, as you can see, and we'll look forward to seeing all of you again February 11th, when we get to listen to Press Jan Ready. And again, please join me in thanking Professor Bradaigh. Thank you very much.